Today we'll get into machine learning by introducing a couple of examples. We'll do one regression example where the response variable is quantitative, and we'll do one classification example where the response variable is categorical. And we'll choose some basic examples of each one. So for regression, we'll look for a function among a space of candidate functions which includes only linear functions. So for example, suppose that you have these 5 training points and you want to find a function that predicts the y value based on the x value for points that are coming from the data generating process that generated these points. 5 is not very many, and it would be very easy to overfit here. One simple way to try to mitigate the overfitting problem is to choose a highly restrictive space of candidate functions, such as the space of linear functions. So we'll only have 2 parameters to adjust, the y-intercept and the slope, and that gives us a function, and the idea is that it should somehow fit these points. To be a little more principled about that, we'd like to minimize the mean squared error for the prediction function. But we can't do that directly because we don't have the probability measure that is generating these points. However, what we can do is minimize the empirical mean squared error. So we assign probability mass 1 over 5 to each of these 5 locations, and then we compute mean squared error with respect to that measure for the particular line that's under consideration. So if the y-intercept is beta 0 and the slope is beta 1, then the mean squared error is proportional to this sum. So we measure the difference between y and the predicted value and square it. And if we put a 1 over n out front here, we'd be taking a mean of those values with respect to that discrete measure that puts mass 1 over n at each xi, yi pair. Since the 1 over n doesn't matter for purposes of optimization, we just discard it and talk about the residual sum of squares. But really this is just proportional to the empirical mean squared error. So problem 1 asks us to find the beta which minimizes this expression. If you look at this expression, if you expand it out, xi and yi are concrete numbers. They're the 5 training observations we have. So we only have 2 quantities here, beta 0 and beta 1, and they're being squared. So this is a quadratic optimization problem in the beta variables. And it's going to have a unique solution because as beta 0 or beta 1 goes to infinity, this squared here is going to send the overall expression to infinity, and it's a differentiable function, so it has to have a minimum somewhere. And what we'll see is that there's just one critical point, and so that will have to be the minimum. So we're going to package things up a bit to make it tidier. As we've already seen, we'll define beta to be beta 0 comma beta 1. So we're packaging these 2 coefficients together into a vector, and we'll consider a vector y, which just has the y values in it. And then for x, what we'll do is put the features that we have, the x values of the observed points, but then we'll augment with another feature, which is just the constant number 1. And the idea there is that we can now write the residual sum of squares as the squared norm of this vector y minus x beta. So the 1s in x hit beta 0 when we conduct this matrix multiplication here. And that produces the beta 0 terms. And the x's hit beta 1, and that produces the slope terms. And if you expand out this squared norm, that's going to be the same as the residual sum of squares. So we can write this out as y minus x beta transpose times y minus x beta. And in this form, we can use our vector differentiation rules to take a derivative and set the result equal to 0. So first we apply the product rule, and that's going to be the first vector transpose times the derivative of the second vector. And the derivative of y minus x beta with respect to beta is just minus x. And then the second term in the product rule is just going to be the same as this one. So we're going to end up with 2 of this term. And setting this equal to 0, we can solve for beta. First we divide by 2 to get rid of the 2. And note that we can't divide by x here because x is generally going to be a rectangular matrix. It doesn't have an inverse. So we can't multiply on the right by the inverse and get rid of it. If we could just say that beta is the solution to this equation, y minus x beta equals 0, and that would be fine, but that would be a situation where we could fit all the data with a line perfectly, and that won't be the situation typically. But we can multiply this out. We get y transpose minus beta transpose x transpose. And again, we multiply both sides by minus a half to get rid of the minus sign and the 2. It's multiplied by x. We multiply this out, and we get y transpose x minus beta transpose x transpose x. And so that tells us that beta transpose x equals y transpose x. Transpose both sides, so we get x transpose x. Beta equals x transpose y. And finally, we get our solution, beta equals x transpose x inverse times x transpose y. So this is called the least squares solution. This is the mathematical form. Computationally, it's much better to, instead of taking the matrix inverse here, it's much better to just do a linear solve. So in code, we would write beta equals x transpose x and then backslash. So that's sort of like the fraction operator, but it goes the other way. So the numerator, if you will, is on the right-hand side. It's not really a fraction because this is a matrix, but that's the idea behind the syntax. So in code, it looks like this. Incidentally, this linear solve operation, it works this way in Julia and in MATLAB and Octave. In R and in Python, you need to use a function called solve. So in Python, it's numpy.linalg.solve, and in R, it's just called solve. And incidentally, the best thing to do is not write out this whole formula. In Julia, just do x/y. And by default, this solves the least squares problem. And the reason you would want to do it this way, aside from there being fewer keystrokes and fewer opportunities to make a mistake, is that it actually uses more direct algorithms that solve the problem more precisely than multiplying out x transpose x in its entirety. So we made this scatter plot. Now let's make the line of best fit. So we'll say beta hat is equal to the x matrix, which we get by putting a column of ones. So that's ones of 5. And then we just put a space in the next. So this is syntactic sugar for horizontal concatenation. We want to have this vector of ones and then the x vector, and we want to put them side by side. And the way we do that is just with array brackets on the outside and then just a space separation on the inside. And then the linear solve operator and y. And then we can just plot this function. Let's do it from 0 to 5. And the function takes as input a variable, let's call it x, and then takes beta hat and dots that with 1 comma x. And we get this line as our line of best fit. So in the second problem, we're asked to apply the same idea, but find a polynomial of higher degree that minimizes the residual sum of squares. The idea here is that if you're looking at a prediction function that's, let's say, a degree 3 polynomial, then this right-hand side, while it's not linear in the x variables, it is linear in the beta variables. There's no betas appearing in products with one another or to higher powers or whatever. This is linear in beta. And that means that you can use the same idea as before. All we have to do, just like we supplemented the matrix of features with a column of ones so that we could incorporate beta 0 into the mix, we just do the same thing by squaring and cubing. We apply exactly the same idea, except instead of just having x to the 0th power in the first column and x to the first power in the second column, we just make more columns. These are new features for our linear regression to use. They sort of don't feel like features because it doesn't require any additional work to collect extra data, but that's fine. These are features obtained by transforming observed features. So let's try to do this in code in a reasonably efficient way. What we're going to do is define a function called bestPoly, which takes a desired degree d, as well as a vector of x values of the observations and a vector of y values of the observations, and then returns a function which is the polynomial of best fit. So we begin by computing our design matrix. And the way that's going to work is we're first going to compute the columns. So we take our original input x, and we just raise it to various powers. So we're going to use the dot version of the exponentiation operator because we're applying this exponentiation to each element of x. So this is the element-wise exponentiation. And we're going to do that for each k from 0, which is the constant term, up to d. So these are the columns that we want. We need to horizontally concatenate those columns. And the way you do that in Julia is with hcat, stands for horizontal concatenation. But the problem here is that hcat expects the columns it wants to concatenate as its actual arguments. So it doesn't take a list of columns and concatenate them. It takes columns as a comma-separated list of arguments and concatenates them. And that's kind of a problem if you're generating the columns programmatically rather than typing them in directly. And there's a solution to this. It's called splatting. So in Python, you would put a single asterisk in front, and that would unpack that list as a list of arguments to the function. In Julia, same idea, but the notation is to put 3 dots at the end. So that expands out this list and supplies its contents as arguments to hcat. Okay, and then just like before, beta hat is going to be x backslash y. And then finally, we're going to return a function, which for convenience, let's just use an anonymous function, which takes an input variable, which we'll call t, let's say, to avoid confusion with this x, but it's the horizontal coordinate. And we'll have beta hat transpose times the monomial, so the various powers of t. So we'll just do t to the k for k in 0 to d. So this takes these coefficients, multiplies them entry by the successive powers of t, and adds up the results. That's exactly what evaluating a polynomial does. And then let's just plot it. Let's make a loop so we can see a bunch of them at once. So for each d, we're going to add to our existing plot a plot of the best polynomial fit of degree d, with x and y as our training points. And we'll put a label on it so we can see which one is which. And to do this, we need to interpolate this value d into this string. And the syntax for that in Julia is a $d like that. And we need to give our x coordinates for the plot, which let's say 0 to 5 in increments of 0.05. And then finally, after we do all of that, it'll create a plot, but it won't show us anything because this plot is happening inside of a for loop. So nothing gets returned from a for loop. And that means nothing gets returned on the last line of this cell, so nothing gets displayed. So we need to ask the plots.jl package to return the value of the current plot, so that when that's returned as the last thing in the cell, it'll actually display. And we get something that looks like this. So our degree 0, that's the best constant approximation. That's just going to be the mean of the y values of the 5 points. Then degree 1 is the line of best fit. We've already seen that one. Degree 2 is a quadratic, which is doing as well as it can to fit the points. And by the time we get up to degree 4, we can actually pass through all the points, because a degree 4 polynomial has 5 coefficients. So this is going to be a system of equations with 5 unknowns and 5 equations. And that's going to be exactly solvable. So there's no empirical error there. Incidentally, this one is curvy enough that we can sort of see the sharp bends, and we could fix that by just lowering the delta. So we need to replot the original plot and then add these new things to it again. And now it's much smoother. So what you can see is that as the degree goes up, we're overfitting to an increasing extent. But the key idea here is that you don't need new ideas to do polynomial regression. You can just use linear regression again by augmenting your feature matrix by raising the x values to successive powers. So in this problem, we'll get to revisit some statistics ideas and think about inference in the context of a linear regression. So the setup here is the same as before. We have some training observations, x1, y1 up to xn, yn. And we define beta hat to be the least squares solution. And we also define y hat to be the prediction. The prediction function maps x to x beta, and so we just call those predictions y hat. And the most compelling part of this problem is in part B, but before we get there, we're asked to think about how we would estimate sigma squared. And sigma squared here is defined to be the variance of this error term. So we define epsilon to be y minus beta x. And we assume for purposes of this model that epsilon is normally distributed with mean 0 and a covariance matrix of sigma squared times the identity. So in other words, for each observation, the observations are independent, and for each observation, epsilon is a mean 0 normal random variable with variance sigma squared. So epsilon is sort of measuring how much above and below the actual line y is. If sigma squared is big, then there's going to be a lot of vertical variance away from the line. And if sigma squared is small, then it's going to be really tight close to the line. It's not related to the variance of y directly, because the variance of y is also controlled by beta. If you have a really steep line of best fit, then the variance in the y direction of y itself would be quite large, but the variance in the y direction of the difference between y and x beta might be very small. So to estimate this vertical deviation around the line, one thing we might do is come up with a line of best fit based on the data, and then measure all of these vertical separations and square them and average them. So our first proposal for sigma hat squared is to take y and y hat, find the squared norm of their difference, and then divide by the number of observations. So this is a good start, but this turns out to be a biased estimator, and we can debias it by subtracting something from the denominator. And if you remember, in the case where we're taking just a horizontal line, so just the ordinary variance of the y component, we needed to subtract 1 because there's a bit of an overfitting problem. The average of the training observations is typically going to be slightly different from the actual mean of the underlying measure. And it also minimizes the sum of squared distances to the point. So it's always going to be a little bit low relative to what you would get if you were subtracting the actual mean. So we divide by n minus 1 to adjust for that. And what happens here is that we're going to have more coefficients. So instead of just a single constant coefficient, we're going to have also a linear coefficient for each feature. And so what we actually need to do here is subtract the number of features. So I'm going to call that value p. And that compensates for this overfitting issue that we're getting sort of a little bit closer to the training points than we really should if we were using the actual underlying measure. In any case, this is going to be our estimator for sigma squared. And with that in place, we can start talking about hypothesis testing for linear coefficients. So in some situations, you're going to have features which have no predictive value. And you want to be able to test the hypothesis that the coefficient for that feature is 0. So the key probability result that allows us to conduct that test is the following. The conditional covariance of beta hat given x. So we're treating the design matrix here as sort of frozen, and we're accounting for the variation in the vertical direction. The conditional covariance of the estimated coefficients is given by sigma squared times c, where c is this matrix, x transpose x inverse. And furthermore, if you take beta hat and you subtract off the actual true underlying value of beta, and then divide by this quantity we call s beta hat, which is s times the square root of the corresponding diagonal entry of this matrix, then that ends up being t-distributed with n minus p degrees of freedom. So what we can do is compute this value under the null hypothesis that the coefficient is 0. We can plug in 0 for beta I. We compute beta hat I divided by s beta hat I, so this is an estimate of the standard error. And we check whether that falls in the critical region for the t-distribution with n minus p degrees of freedom. So let's start with 100 observations and 10 features, and we'll just make up our features at random. And then we'll combine them in this particular way. So the second feature, along with the fifth and seventh feature, are contributing with these weights to produce the resulting y vector. And epsilon has a standard deviation of 2.1. At first, let's look at the sixth feature. Compute beta hat, compute c, which is the inverse of x transpose times x. We compute sigma hat, which is the estimator of sigma, and that's going to be given by the norm squared of x minus beta hat divided by n minus p, but that's the estimator for sigma hat squared. So if we want sigma hat itself, we square root that, which we'll do by just peeling off the squared in the numerator and then putting a square root in the denominator. And then we can compute si for this particular feature, I equals 6. It's going to be beta hat I, so we're just doing what we're told here. Pull out the ith component of beta hat and then divide by s times the square root of the I comma I component of c. And then to conduct the hypothesis test here, there are various ways to go about it, but one thing we can do is compute a p-value by evaluating the CDF of the t-distribution with n minus p degrees of freedom at the observed statistic si. And then this is going to be an extreme p-value if it's less than 0.025. Let's say we're using the 5% significance level, so this is 5% divided by 2. If it's more extreme than that, or more extreme on the other end, then we'll reject. Otherwise, we fail to reject. So let's run this. So we fail to reject here, which is good because this coefficient is 0. If we run this a bunch of times, eventually we would reject, but we make mistakes sometimes. There it is. So we happened to get data that made this coefficient seem large enough that it was reflecting an underlying non-zero value. And we rejected the null hypothesis, even though the null hypothesis was actually accurate. So that's going to happen about 5% of the time on average. if you're working at the 5% significance level. If you look at a coefficient that does work, like I equals 7, then sometimes we are going to fail to reject anyway, and it's going to be more than 5% of the time in this case. So we've gotten 3 fail to rejects and 2 rejects. That's indicative of this test not being very high power. When you only have 100 observations and 10 features, there are going to be times when you can't really tell and you have to fail to reject, even though the underlying coefficient is non-zero. If you have many more columns, or if this coefficient were larger, then you would be getting higher power and you'd be telling what's going on much more accurately. So for example, if we step it up to 10,000 observations, then we're going to reject much more consistently with that coefficient, which is in fact non-zero. And we're going to be estimating the coefficients quite accurately as well. So these two coefficients were 1 and -1, and this coefficient was -2, and you can see they're approximated quite accurately. And these other bars are fairly close to 0, and this test is telling us about how close to 0 to expect them to be, just based on random fluctuations in the data, given that in the underlying model they're actually 0. So in this section, we're going to look at a classification problem. So suppose that we have messages coming into our inbox, and 80% of them are spam messages, and 20% of them are legitimate messages. And we have a function that computes a spam score, which is supposed to be indicating how much we think it's spam. And it's not perfect, so there ends up being some overlap where some legitimate messages have higher spam scores than some spam messages. And the idea is that we want to just predict for each message, is this legitimate or is this spam? And the loss function that we're going to use is just misclassification. What's the probability that I get it right when I get a particular message to classify? So what you can see pretty clearly is that if you have a spam score that's like 10, you're well in this region where the messages are legitimate, and so you should classify it as legitimate. Whereas over here, it definitely looks like spam, so you should classify it as spam. And in between, it's more murky. But the crossover point is in fact exactly where these graphs cross, because the conditional probability of one class or the other is going to be determined by the heights of these two graphs at that particular value. So there's more probability density at this value of, let's say, 13 coming from legitimate messages than there is coming from the spam messages. So to find the threshold where to the left we should classify as legitimate and to the right as spam, we just need to find where these probability densities intersect. And we have to give a starting point looking for this root, so let's just say 15, because that looks like about what it is from the graph. And we get 14.92 as the crossover point. So I want to say something about this visualization. Neither this red nor this blue curve are probability density functions, because the total amount of mass under the red curve is 0.2, and the total amount of mass under the blue curve is 0.8. So what I'm doing here is displaying the full probability measure. So there is one total unit of mass here, 0.2 of it there and 0.8 of it here, but I'm displaying it in different colors. So it's like we take the probability mass and sort of paint it according to its classification. And that gives us two separate graphs here, but there's still one probability measure. The way we would sample from this measure is we would draw a color with probability 0.8 of being blue and 0.2 of being red, and then draw from the corresponding distribution. So from this distribution if we drew red, and from this one if we drew blue. So let's step it up into 2 dimensions. Let's suppose that we have 3 colors of flower: a green flower, a blue flower, and a red flower. And they have different prevalences. So half the flowers in the field are blue, a sixth are green, and a third are red. So we're going to need to take that into account. But conditioned on color, the distribution is going to be multivariate Gaussian with particular mean and covariance matrix that we're going to know. So the means here are given by these 3 vectors for the 3 colors, and the covariance matrices are given by taking these 3 matrices, each one, and multiplying it by its transpose. So AR transpose is going to be the covariance matrix for the red distribution here. And the reason we set it up this way is it makes it easy to sample. We can just take the mean and add it to A times Z, where Z is a vector of independent standard normals, and that's going to give us a set of observations from the red distribution, and similarly for the other colors. So visually here, what we can see is that like the green ones are really concentrated here. If we see something up here, we're probably going to predict it's green. The red ones are sort of down here-ish. Something kind of in that zone is probably going to be red, and then pretty much everything else is going to be blue. Blue gets a leg up in sort of ambiguous regions because of this extra prevalence. So if we want to visualize this distribution, we can make a surface plot of the density. So what I've done here is multiplied the PDF for each normal distribution by the corresponding frequency p, and we get this graph. So if points land here where the blue curve is the biggest one, then we're going to predict blue. If they land here where the red surface is higher, we're going to predict red, and if they land anywhere here where the green surface is higher, we predict green. And if we turn this around a bit, we can start to see where these surfaces intersect each other. There's this sort of ellipse here, or maybe actually it looks more like a hyperbola type shape. Maybe a parabola here for the red. There's an ellipse here where the green is the biggest, and then everything else is blue. So this is the two-dimensional figure that's corresponding to this figure for a single dimension. So we begin by randomly sampling our flowers. We'll do this in kind of a fun way where we make a struct for a flower. So it's going to contain a vector, which is the feature, as well as a color, which is the label, and we'll encode the color as a string, just red or green or blue. So the rand flower function, it chooses the color based on this weight vector, and then you make a flower which has as its feature vector the corresponding az plus mu value, and then the selected color. So if we look at our flowers here, it's just a 300 element list, and each one is a flower object with a particular feature vector as well as a label. So let's start by making a prediction function. If we have a particular feature vector together with a set of probabilities for the three classes, together with a set of distributions for the three classes, then what we can do is calculate p times the probability density there for each of the classes. So we zip the probabilities and the normal distributions and compute the corresponding probability mass for each class. And then we just compute the argmax of that. So we figure out which index has the biggest value of p times the density there. Next, we'll make a function called classification plot, which makes our full plot for us. So it's going to take as its first argument a function which we'll call predict. Then it's going to take as its second argument a list of flowers, then a list of probabilities, and then a list of normal distributions. So we can make a plot that shows the different classes in sort of a cheap way by choosing a heat map with a color gradient that has a number of colors equal to the number of classes. So we have three classes here. We'll do a heat map with three colors, and that's going to make every point in the heat map be exactly one of the three colors. We have our x's and y's that were already declared up here for our plotting purposes. And then the function we're going to plot maps each x comma y compared to the prediction at that particular x comma y value. And then we'll use a color, which is a color gradient built out of our three colors we want to plot with. We'll adjust our opacity, aspect ratio of the plot, take the legend out of it, and make it square, let's say 400 by 400. For each color, let's make a scatter plot of that particular color for the flowers that have that particular color. So we're going to add to this plot that we already started making, and in plots.jl, the way you do that is you supply the plot you want to add to as your first argument. So the points we want to scatter are the feature vector of the flower f, but realized as a tuple. So we have parentheses here delimiting this point, where f ranges over the flowers. And we're going to select out the ones that have that specific color. So we'll do that by putting an if clause into this array comprehension. And then we'll supply a color to the scatter function. So this is what we get for this example. Our blue flowers are here, green here, and red here. And you can see that some things are being classified incorrectly, even though we're using the best classifier possible. We're using knowledge of the underlying probability measure. So based on the feature vector you get, this is literally the best prediction possible. This particular flower, for example, should be predicted to be blue because it is more likely to be blue based on the observed features. But there's just some probability of misclassification whenever you have overlapping probability measures, and that's what's going on here. But what we can do is check how many are correct. Let's define a function called correct, which takes a list of flowers, a list of probabilities, a list of normal distributions. And what we want to do is count the number of colors that are predicted correctly. So we're going to loop over the flowers, and then for each flower we're going to check, is its actual color equal to the predicted color? So we predict, and then the thing is, this prediction returns an index rather than a color string. So we need to make it into a string by indexing this colors vector. And then we're just going to count the number of truths in that array, and then we can take off these brackets to avoid allocating an intermediate array. And then we can actually call this function with the flowers we have, and we see that we get 265 of the 300 correct. So we sort of cheated here because we used the actual probability density function for the measure that's generating these data, which is shown here. And what we'd like to do is figure out how to look at the original data and come up with that estimate. So for example, looking at these observations here, and come up with that estimate without having to cheat and know what the underlying probability measure is. And you can do that in various ways. The goal is just to estimate the probability density. And one way to do that would be to use a kernel density estimator. So you just, for each separate class, you estimate the density for that class. You end up with a red kernel density estimator, a blue one, and a green one. And then you just use those density estimates instead of the actual density. Another thing to do though here, especially still cheating a little bit since we know these are coming from multivariate Gaussian distributions, but you could do that anyway. Just look at the data, it sort of looks multivariate Gaussian. You just decide you're going to fit a Gaussian to each of these and then use those densities. And of course you're going to get very good results that way because the assumption that the data are multivariate Gaussian is in fact accurate here. Let's make a function that estimates a density for each color. So let's call it MVN estimate. And the two arguments are going to be flowers and color. So the first thing is we're going to pull out the flowers that have that particular color and just look at the feature vectors. And then we're going to estimate the mean. So I'll call it mu hat, and that's just going to be the mean of these feature vectors here, f dot x. So those are vectors, so they can be added and divided by how many there are. That's what the mean function does, so it's no problem. Then we want to form an estimate of the covariance matrix, and we can do that by kind of following the same idea. We compute x minus mu transpose, except since we don't know mu, we'll just use mu hat instead, and average that over all the flowers. And the reason we're using x minus mu transpose is that's just the formula for covariance matrix. The definition of the covariance matrix of a random vector x is expectation of x minus mu transpose. And we're just using that here with this Monte Carlo approach based on the observations that we see. So in the same way that we have to estimate the density, we also have to estimate the proportions. And we'll just do that in the straightforward way of counting how many reds, greens, and blues we observe in our data set and using those as estimates. So we'll just extract our colors across our data set and then count map that. So that's doing a tally. So we'll get 145 blues, 51 greens, and 104 reds in this case. And then we'll estimate our proportions just based on that. So we'll do color counts, C divided by length of flowers. So that's the proportion that are that particular color. And we do that for each color. So those are our observed proportions. So they're pretty close to the actual proportions, 1/3, 1/6, and 1/2. So let's make a vector of our multivariate normal distributions using the function that we defined. So we just get 3 multivariate normal objects with some mean and covariance matrix. And then since we made our classification plot a function, we can just call it again rather than having to type that code again. And this is what we get. So we see that it's very close to the optimal prediction function, which is here. I mean, just looking at it back and forth, you can barely tell the difference. And the reason it did such an effective job is because we have enough observations from each color to do a good job of estimating the proportions and the distribution that they came from. And since they actually came from a multivariate normal distribution, we get a very accurate picture of the density based on just estimating the mean and the covariance matrix. So in summary, linear regression in its basic form asks us to find the beta hat that minimizes the residual sum of squares, which is the vector of y responses minus x beta, where x is the matrix of features, also known as the design matrix, which consists of usually ones in the first column if we want to have an intercept term, followed by the x observations in the next column. And then if you have more features, then there would be more columns here And you can also include derived columns, which are computed as functions of the original observations. The other thing we learned is that we can use the t-distribution to test the hypothesis that one of the coefficients in our linear regression is 0. We also talked about classification problems, and the main idea there is that the predictor which minimizes misclassification probability looks at the conditional probability of being in a particular class, which is proportional to the overall probability for that class, and then the class density for that class. And then the second point we made is that to estimate this value based on actual data, we just need to approximate these two quantities. So typically we would estimate the proportions for the classes as the proportions of class I observations in the training data. And then estimating densities is a trickier thing, and there's more flexibility in how you would do that. So for example, you can use quadratic discriminant analysis, which just assumes that the class conditional densities are multivariate Gaussians, and then you use the training data to estimate the means and covariance matrices for those class conditional distributions. Or you could use kernel density estimation. Or you could use any other means of estimating densities.